Hello everyone, welcome to this class on finite element analysis. And in this class, let's learn this problem on beams, on analysis of beams. In this, we have a cantilever beam subjected to a point load of 250 kilonewton as shown in the figure. Determine the deflection at the free end at here and the support reactions. Support reactions, it is this. So take Young's modulus E equal to 200 GPa. I is the moment of inertia, which is 4 into 10 to the power of 6 mm to the power of 4, and they have given the length of this element as 0.8 meters. So first let's try to write the given data. So the given data is only this. So E is 200 GPa and I is 4 into 10 to the power of 6 mm to the power of 4, and LE is 0.8 meters. So now it is very important that you have to convert all these SI unit or all these parameters into common units. That is, everything has to be in either in newtons and in millimeters. Okay, so here this one I've already taught you in analysis of bars. If you have doubt, you can just check my video on analysis of bars. This gigapascal, when it is converted into Newton per mm square, it is nothing but 2 into 10 to the power of 5 Newton per mm square. And here it is already in mm4, and here Newton and mm square. This one, if I'm converting it into mm, I'll get 800 mm. So this is all about the conversions. Okay, now let's try to find the solution for it. The solution, the first step is always the FEA model. So the FEA model for the beam is, at every node there are two displacements. One is a vertical displacement, another one is a horizontal displacement. So the beam element for the FEA model is written like this. So here there is a vertical displacement as well as there is a angular displacement. There is a vertical displacement here and an angular displacement. This is node number 1 and this is node number 2. At node number 1 you have Q1 as the vertical displacement, Q2 as the angular displacement. Similarly here you have Q3 as the vertical displacement and Q4 as the angular displacement. And this one is taken to be the length of the element. Length of the element is 800 mm. So this is all about the FEA model. The second step is, so this is the first step. The second step is elemental stiffness matrix. Elemental stiffness matrix. Elemental stiffness matrix. So the elemental stiffness matrix, so that is given by Ke equal to Ei by Le cube. So you have to write like this. You can just write 12 6 6 4, 12 6 6 2, 12 6 6 2. The same thing is replicated here, 12 6 6 and 4. So this is how I remember. And here you can add Le square, not here, Le and Le square. Similarly Le and Le square, and here it is Le and Le square, and here you can put it negative, and similarly here it is negative, and here. So these terms are considered as negative. So now there is only one element, therefore that is going to be K1. If there are two elements, you should have found out K1 and K2, but there is only one element. E is nothing but 2 into 10 to the power of 5. 2 into 10 to the power of 5. I is 4 into 10 to the power of 6. Well, Le is 800 cube. And let me try to substitute that. 12, 6 into 800. 6 into 800 is 4,800 minus 12. 6 into Le again is 4,800. 4,800 again, and Le square. So that is going to be a very big number there. 4 into Le square. That 4 into Le square is nothing but 800 square into 4. So 800 square into 4 will be 2,560 into 10 to the power of 3. Next, 6 into Le, minus 6 into 4, minus 6 into 800 is minus 4,800. And here is 800 square into 2 is nothing but 1280 into 10 to the power of 3. You can just put those values into calci. That is Le square, 800 square into 2. And here it's going to be minus 12. And here it's minus 4,800, 12, and again minus 4,800. And here it's going to be 4,800. And here it's going to be 1280 into 10 to the power of 3 and minus 4,800, and here it's going to be 2560 into 10 to the power of 3. The next step is actually the global stiffness matrix, but in this problem you can clearly see there is only one element. Therefore, this elemental stiffness matrix, which is nothing but ESM, that itself is going to be equal to GSM, that is global stiffness matrix. Therefore, the third step, K equal to K1, which is nothing but the global stiffness matrix. I'm going to write it as GSM. But in the exams, whenever you can write it in the full name, global stiffness matrix. So let me try to write it here. That is nothing but the global stiffness matrix. So which is nothing but going to be the same. And here, this value, when you have to simplify that. You have to simplify and try to write it as one value. So when I try to simplify this, all 2 into 4, 8, 8 divided by 800 cube, and here it's 10 to the power of 11, all that. So this one I'm going to get it as 1.56 into 10 to the power of 3. So this I'm going to get it as 1.56 into 10 to the power of 3. So let me try to save my time in the exam. So let me not try to write all this again. So all this simplification together, it's going to be 1.56 into 10 to the power of 3. This 1.56 into 10 to the power of 3 is common to every element into this matrix. I hope you have understood. So let me just go to the next step. The next step is very much clear. The next step is very much clear. Here you can just see it is just a point load. If there is a point load, you can directly write the global loadal vector and global displacement vector. So first let me write the global displacement vector. The global displacement vector Q equal to, so just see from the problem how many displacements are there. There are totally 4 displacements, 1, 2, 3 and 4. At every nodes there are 2 displacements. Therefore, for 2 nodes you get 4 displacements. Therefore, I can write this as Q1, Q2, Q3 and Q4. Similarly, the global loadal vector or global load vector, that is going to be which is nothing but equal to F1, F2, F3 and F4. So from the figure you can just directly observe here, if there is a vertical displacement over here, there should have been a vertical force. If there is a angular displacement, there should have been an angular force, but here it is absent. Therefore you can take F1 and F2 to be 0, and because of this vertical displacement there is a vertical force over here, that is 250 kilonewton, which is acting downwards. Whenever it is acting downwards, you can consider it to be negative. And here finally you have Q4. There is nothing like angular force over here, therefore that is F4 is considered to be 0. Only F3 is considered to be 250 kilonewton, that is minus 250 kilonewton, as it is acting downwards. So you can mention it here as well, F3, because though it is acting at node 2, the third displacement, because of the third displacement Q3, you have a third force, that is minus 250 kilonewton. Minus because it is acting downwards. So please remember that minus 250 into 10 to the power of 3 newtons. So minus 250 into 10 to the power of 3 newtons. So let me try to write that. Minus 250 into 10 to the power of 3 newtons and 0. So now it is very much clear. The next step is the fourth step, that is equilibrium condition. Equilibrium condition. In equilibrium condition, the formula is going to be clear, that is K into Q, which is equal to F. So this is Q, this is F, and K you have got it as this matrix. So this is nothing but the global stiffness matrix K, which is equal to K1, which is this one. This value, that is 1.56 into 10 to the power of 3 is going to be common, and this matrix is what has to be written. So let me try to write that first. Okay, you can just see I have just written out this K into Q, which is equal to F. And now you have to use this elimination method over here. You have to use elimination method to apply the boundary conditions okay. Use the elimination method and apply the BCs. BCs are nothing but the boundary conditions. So here you can just see the boundary conditions. Here node 1 is fixed. If node 1 is fixed, the Q1 and Q2, that is the 1 and 2, that is Q1 and Q2 or F1 and F2, or all those that belongs to 1 and 2, that will be made 0. That means in elimination method, you have to delete first row, first column, second row, second column. The reason is at node 1, Q1 and Q2, there are 2 displacements. Therefore, the ones that is related to 1 and 2 must be eliminated. And at node 2, it is a free end. There is nothing, it's neither fixed or any other support is there. There are no any supports at node 2. Therefore, node 2 is left free. But node 1 is going to be eliminated. Node 1 in the sense, the displacements 1 and 2, that is related to 1 and 2. So therefore first row and first column, second row and second column is eliminated, because node 1 is fixed, and at node 1 there are two displacements 1 and 2, that is q1 and q2. Therefore I'm going to eliminate this first column and first row, and also second row and second column. So they will be eliminated. Now let me try to write the remaining elements of this matrix. So 12 minus 4800 minus 4800 and 2560 into 10 to the power of 3. So this 1.56 into 10 to the power of 3, that will be retained as it is, and here q3 and q4, that will be written, and here it is going to be minus 250 into 10 to the power of 3, and here it's going to be 0. So all these are going to be written. Now let me try to apply the whatever this matrix multiplication. So 12 into q3 minus 4800 into q4. So here this 1.56 into 10 to the power of 3, that will be taken common to this, that is nothing but equal to minus 250 into 10 to the power of 3. And similarly minus 4800 q3 plus 2560 into 10 to the power of 3 q4, that will be multiplied, and again 1.56 into 10 to the power of minus 3, that will be taken common, that is nothing but equal to 0. Now you have to use your calculator modes. So let me try to use the calculator. In calculator you have to just take this modes. The modes are nothing but going to be, so just take mode. So let me just take equation and give the number of unknowns as 2 unknowns. There are only q3 and q4. The number of unknowns are 2. So therefore the number of unknowns are 2. So it is going to ask for a1. So this is, you can take this as a1, this as b1, this as c1, a2, b2 and c2. So let me try to give that. So a1 is so let me try to keep it here. So a1 is 12, b1 is minus 4800, c1 is minus 250 into 10 to the power of 3, and a2 is minus 4800, b2 is 2560 into 10 to the power of 3, and c2 is 0. So once I do that, I'm getting the value of x. X is nothing but q3. So q3 is found to be 83,333, 83,333.33, and q4 I'll get it as 156.25 minus 156.25. But the problem isn't over here. You have to divide this 1.56 into 10 to the power of 3 with this to get that answer. 1.56 into 10 to the power of 3. So that you have to go. So it's plus 3 over here. So let me try to get that answer finally. So 83,333.33 divided by, so I'll just put 1.56 into, I'll just put 1000 for 10 to the power of 3. So the answer is going to be 53.41. So let me just try to do it again. So 83,000. Okay, so the answer is found to be 53.41. So let me write that answer. Q3 is 53.41 mm, and Q4 let me try to do that. Minus 156.25 divided by 1.56 into 1000. So the answer is found to be minus 0.1, and the SI unit for Q4 is going to be radians, because Q2 and Q4 at nodes 1 and 2 are angular displacements, and for angular displacements the SI unit is always radians, and for linear displacements the SI unit is always millimeters. So in this problem they have just asked determine the nodal displacements. So determine the deflections of the free end and the support reactions. Okay, let me try to write the support reactions as well. So that one, so when you just find out this Q2, Q3 and Q4 is found to be so much. So let me try to do the support reactions. Okay, now I have just written to find out the support reactions R1 and R2, because only at the node 1 we have the supports. For example, only at node 1 you have support, therefore only R1 and R2 have to be found out. That is related to 1 and 2. You don't have to find R3 and R4. So let's try to be smart over here, because this matrix is going to be multiplied with this. So you don't have to multiply every element. So just multiply wherever zeros are not there, because any element multiplied with zeros will remain zero. So you have two zeros over here. So let's try to be smart over there. So let me try to find out r1. So when I try to find out r1, just try to check it out once. So just check it out. 12 into 0 is going to be 0. 4800 into 0 is going to be 0. Minus 12 into 53.41. Minus 12 into 53.41. Plus 4800 into minus 0.1. So that is going to be minus here. KQ minus. So minus, let me say 0 or something. So minus 0. So because for r1 that's not going to change anyway. So let me just try to calculate that data. So r2, let's try to find r2. 4800 into 0 is going to be 0. This one multiplied by 0 is going to be 0. You're just going to put minus 4800 into 53.41. This element, third element multiplied by third element over here. First element by first element, second by second, third by third, fourth by fourth. So for second row we are doing 4800 first element into this is 0. 2560 into 10 to the power of 3 into 0 is 0. Minus 4800 into 53.41 directly I'm writing. And 1280 into 10 to the power of 3 into 0.1. So it's minus 0.1. So let me just try to put it minus 0 directly. So minus the 0, this second element is going to be 0. So here what I'm going to do, let me try to put that. So here this minus I'm going to replace it here. So here I'm going to remove it. So similarly, okay, now. So let me try to simplify this. So let me see what I'm going to get here. So minus 12 into 53.41 minus, open the brackets, 4800 into 0.1. So it's found to be minus 1120.92, minus 1120.92 newtons. So R1. So R1 is found to be so much. Now similarly, let's try to find out R2. Minus 4800 into 53.41 minus 1280 into 1000. So 10 to the power of 3 I'm writing like this into 0.1. So that is found to be 368 minus 368 newtons. So thus we have found out the reactions as well as the displacement at both the nodes. I hope you have understood this. So here we have found out the displacements at node 1 and node 2, as well as, that is at not at node 1 and node 2. At node 1 as it's fixed, it's going to be 0. At node 2, the vertical and the angular displacement, and the reactions at the supports, that is only at node 1, that is R1 and R2. You have to find out both at node 1 itself. So I hope you have understood. Thank you so much. Take care.